Okay, in class today, we're looking at graphs and trying to figure out their end behaviors. Okay, so what's going on to the far left of the graph, and what are the y values doing to the far right of the graph? Okay, so whenever we're talking about behaviors, we're talking about the y values at specific x values. Okay, good to know that these are all about the y values. So our first example here is a cubic function. So hopefully you know that a cubic function is anything raised to the third power, right? The highest degree of your function is the third power, okay? Cubic, right? Third power. So we're being asked about the left end behavior and the right end behavior. Okay, so we're going to use some special notation for this. We're going to talk about as x approaches infinity. Okay, so there's some things that we probably might have not seen. X, arrow, infinity. In fact, left end, so it's x arrow negative infinity. On the left side of the graph, that's the negative x infinity sign. Okay, so this here, this symbol that we see, this symbol means as x approaches negative infinity. And like it says, we're talking about the left end behavior, so this is what's happening on the left side of your graph. Okay, so we're basically looking for what are the arrows doing. Okay, so if we're looking at the arrow on the left side of the graph, in what direction does the arrow point? The arrow points down, and whenever our arrow points down, that means our y values are going to negative infinity. Okay, so as x goes to the left, right, the left side of the graph, the y values, which we call f of x, of course, also go to negative infinity. Okay, so this says that our graph arrow points down. So it's important to understand what these symbols are talking about. Right, so on the left side of the graph, the y values are going down. They're getting larger but negative. Larger negatives on the left side of the graph. Okay, and then right end behavior means what's going on the right side of the graph when x are very, very large positive values. So we use the same notation as x approaches positive infinity. Okay, so on the right side of the graph, we have positive x values, so we have positive infinity. Okay, so what are the arrows doing on the right side of the graph? Pointing up. Now, if the arrows point up, that means that they're going up there to positive infinity. So the other thing about our graph is the zeros. So the zeros of the graph are where your graph crosses or touches the x-axis. So on our graph, we see that there are 3 places where it crosses the x-axis. Once at -2, once at -1, and once at +1. Okay? So our cubic equation will have at most 3 x-intercepts. Okay, so for the zeros, we write x equals -2, -1, and +1. Okay, so let's answer those questions here for our middle graph. Okay, this is called a quartic function. A quartic has as its power a 4. So this is some type of an x to the 4th power. Right? Think about quarters, has the same root word. Quarter is something divided into fourths. A quart is 1/4 of a gallon, right? 1/4 of a gallon. So this word quartic is a 4th degree power. So this is going to be an even polynomial, right? Because we have an even power as the degree. So over here, this must have been an odd polynomial because it had an odd power. It's something to understand about because all evens and all odds basically behave the same. So what do you notice about the arrows of this 4th degree polynomial? They go up. Not only do they go up, they both go up. Okay, and this happens with all 4th degree polynomials as well as 2nd degree polynomials. So all even polynomials always have the same end behavior. Both arrows either point up if it's positive, or both arrows point down if it's negative. Okay, so that is a property of all even polynomials, is that their behaviors, your left and your right hand behaviors, are the same. And now let's look at the zeros. Where does this thing cross your x-axis? Right in there and at positive 2. Okay, so we only have two zeros in this case. X equals 2.5, negative 2.5, and positive 2. And now for our third graph, okay, a quintic. Quintic is like quince, right, which is 15 in Spanish, but quintic is actually just going to be to the fifth power. So it has the same root word as quince and cinco and those other ones. So this is an x to the fifth. 5 is an odd number, so this is an odd polynomial, right? Notice the arrows of this odd polynomial compared to our others. On the left side, the arrow goes down. On the right side, the arrow goes up. Okay, so for our fifth degree, look, the arrow goes down on the left, and the arrow goes up on the right. Okay, so all odd polynomials basically behave the same, just like the x to the third. Now we have how many zeros here? We have 1, 2, 3, right? This is where it touches. Even though it doesn't cross the x-axis at positive 2, it does touch there. So that is, in fact, a 0. So we have 4 zeros, starting at negative 4 and negative 2 and positive 2 and 5, just like that. So now let's talk about the multiplicity, right? This is a good vocabulary word. So notice, like we set up here, a third degree should have 3 zeros. Right, 1, 2, 3 zeros, 3 places where it crosses the x-axis because it has a power of 3. Now notice this one had a power of 4, but how many times does it cross the x-axis? Only twice, which means one of these has to be a multiple root. Okay, a multiple. That's what it talks about with the multiplicity, is that one of the zeros is a solution multiple times. Okay, like here we have 1, 2, 3, 4, but we're supposed to have 5, so one of these is going to be a multiple root. Okay, so multiple roots greater than 1 have a special thing with the graph. So let's see if we can define this, probably not very well, but very informally. The multiplicity of a 0, okay, is where one root is used multiple times, right? It's multiple times as the solution. And that's where we get the term multiplicity. Okay, so we'll look at this. So here's some words about our graphs up there. And the first one, all the zeros have a multiplicity of 1, right? So look at what happens when they have a multiplicity of 1. So we'll talk about this in a second on the second page. This one has a multiplicity of 3, right? So 2 is a triple root because it is represented there 3 times. And then here it says 1 has a multiplicity of 2. I guess the 2's over here. Okay, so they're different graphs. The graph behaves differently depending on the multiplicity. Okay, so that's what we're going to talk about on the second page of this worksheet. So let's go over to that. So the first question asks, what do you notice about the sum of the multiplicities? Sum of the multiplicities and the degree. Okay, so what we're going to find out if you study this and you look back at them, you'll find out that the sum of the multiplicities is equal to the degree. Okay, the sum of the multiplicities equals the degree. So if we were to add up all the multiplicities of your zeros, that would be the same as the degree of your polynomial. Okay. Oh, by the way, when we write this in factored form, it's really important to understand that we're going to have some type of a factor, right? X plus 2, x minus 3, 2x plus 5, right? Some type of a factor. You're going to find the multiplicity up here in the power. Okay, this is where we're going to see the multiplicity. The power of the factor. The power of the factor is the multiplicity of the root. Okay, so it's the power. When we're looking at an equation in factored form, the power of that factor is the multiplicity of the zero. Okay, so let's go back over here and we'll write down some of the factors from your x-intercepts. Okay, and we know how to do this. Okay, so if I have a -2 as a 0, that gives me an x plus 2 as a factor. If I have a -1, 0, that's an x plus 1 as a factor. If I have a +1, 0, that's a -1 as a factor. Right? So notice, do we have any powers on any of these factors? Right? Do you see a number up here or a number right there or a number right there? Right? We don't actually see one, but because there is a parenthesis there, we can assume that the factor is a 1, right? The power of each of these factors is 1. So that said, what is 1 plus 1 plus 1? 3, right? So if you add up the multiplicities, if you add up the powers of all of your factors, that needs to be the same as the power of your polynomial, the degree of your polynomial. Okay, so that's what that first part says, is that if you add up all the multiplicities, that should be the same as the degree of your polynomial. Okay, so what if the multiplicity is 1? So here are the vocabulary words we're going to use. With a multiplicity of 1, the graph will cross the x-axis. At x equals whatever, right? At whatever that x solution is, it will cross. So the word we're going to use to describe the behavior of the graph is cross. Okay, the graph will cross. That's the behavior. When you're describing the behavior, the word is cross. The graph will cross the x-axis at that point. Okay, the next one, with a multiplicity of 2, what's the behavior? So with a multiplicity of 2, the graph will, the word is bounce. Bounce at that x value. Okay, so at a multiplicity of 2, the graph is not going to cross. The graph will not cross the x-axis at a multiplicity of 2. Okay, so let's take a look at what that would look like as a little sketch. So there's your y-axis, here's your x-axis. So our graph is going to touch. So maybe that's our 0. Then the graph will come down and touch right there and then go back up in the same direction it came from. Okay, it does not cross the x-axis. It bounces. Okay, or potentially it could bounce from the negative side, right? It comes up and it touches. That's supposed to touch right there. It touches at that 0, but it does not cross the x-axis. Okay, it does not cross the x-axis when we have a multiplicity of 2. So let's come over here at this graph, this third one. Notice where the bounce is. Okay, here at +2. That's where the graph bounces. So if I were going to write this equation as its factors, I would write x plus 4 for a -4, 0. I would write x plus 2 for a -2, 0. I would write x minus 2 squared because it bounces. It bounces here, which means I have a multiplicity of 2. And then at 5, I would write an x minus 5. Right? None of these other ones would have powers because at all of these other zeros, the graph crosses, right? From top to bottom, it crosses at all those other places, even with a multiplicity of just 1. So if I were to add up all the powers, right? 1 plus 1 plus 2 plus 1, that is a power of 5. And the sum of the multiplicities equals the degree of the polynomial. So a multiplicity of 2 means the graph bounces. It does not cross the x-axis, but it hits it and goes back the other direction. And then our third type is what happens if we have a multiplicity of 3. Okay, so if we have a multiplicity of 3, the graph will flatten at that x value, but it crosses. The graph will flatten as it crosses the x-axis. Okay, so our 3 vocabulary words to describe behavior are cross, bounce, or flatten. Okay, we either cross if it has a multiplicity of 1, we bounce if it has a multiplicity of 2, which means it does not cross, or it flattens if we have a multiplicity of 3. So let's come over here. Oh, it does say 2. My bad. This is supposed to say 3. Excellent catch, world. 3. Multiplicity of 3, the graph will flatten as it crosses the x-axis. So there's an example here in the middle one. Right, this middle graph here, notice how our line crosses but does not cross very steeply. Okay, that is how we're going to represent a flattening cross. So we have x plus 2.5, and we would have x minus 2 to the third power. Okay, that would have a power of 3 because of this crossing at a flat rate here, right? That represents a multiplicity of 3, a power of 3 on your factor. And this one, of course, has a power of 1. 1 plus 3 is 4, and that is the degree of your polynomial. Okay, so that's some important stuff to understand and make a connection between the graph, what is the behavior of the graph at the x-axis, and what does the equation of your polynomial look like. Okay, so we're going to take away the graph for a second and ask you the same question, but with just an equation. Okay, so it says, how many times is x plus 1 a factor of this polynomial? Okay, so what we're going to do in order to figure that out is synthetic division. So first we start with the roots. In order to find the root, you set your factor equal to 0 and you solve. So if I have a x plus 1 factor, that means I have a minus 1 or a negative 1 root. So we're going to use synthetic division with negative 1. Okay, and what we're looking for is a remainder of 0. So I have a 1, and then a 2, and then a minus 1, and a minus 2, right? Those are my coefficients of my polynomial, my cubic polynomial. Okay, so we're going to synthetically divide this here and look at the 0. So we get a remainder of 0, which means negative 1 is in fact a root. So to test and see if it's a root again, we're going to use synthetic division with these numbers, 1, 1, and minus 2. Okay, so we continue using negative 1 as your synthetic division on your new quotient, right? This is the quotient, the polynomial we get when we divide something. So what do we get when we do synthetic division there? We notice that we get negative 2 as the remainder, which means negative 1 is only a root once. So this has a multiplicity of 1. And describe the behavior of the graph at this root. The graph will cross the x-axis. At x equals negative 1. Okay, a multiplicity of 1 means our graph crosses, right? That's our vocabulary word for the behavior of the graph with a multiplicity of 1. Okay, so we can look over here at the graph, actually, and see at negative 1, the graph does in fact cross exactly as our math indicated. Okay, so it's a good thing to be able to verify your math with a graph, but we won't always have a graph, will we? Nope, we won't. So we got to be able to trust your math. So if I had x minus 1 as a root, as a factor, what is my root? Positive 1. Okay, you always want to set your factor equal to 0 and solve in order to get your roots that we're going to use synthetic division with. Okay, so I had a 2x squared minus x squared, 2x cubed minus x squared minus 4x plus 3. Okay, so we're using this polynomial and synthetic division to figure out how many times 1 is going to be a root. Okay, so let's use synthetic division and see what we get. And we get a 0. So we do synthetic division again with these red numbers, right? But we never use our remainder. Your remainder is not a part of your quotient anymore. So let's use positive 1 again to see if it's a double root. And yes, we get a remainder of 0, which means that it is at least a double root. So now let's see if it's a triple root. So we're going to do synthetic division with 1 on these two remaining numbers, right? Just 2 and 3. And notice that we get a 5. So that means that 1 is only a root twice. Okay, so it has a multiplicity of 2. And if it has a multiplicity of 2, then the graph will bounce at x equals 1. Okay, so the vocabulary word for our behavior is bounce. And let's look over here at the graph and see what's happening at x equals 1. And sure enough, the graph shows that we go down to positive 1, and then it bounces and goes back up. So yes, we have a multiplicity of 2 at x equals 1. Okay, so we're going to do more and more and more with graphs and their multiplicities and writing powers and polynomials from graphs based upon how the graph is behaving on the x-axis and on the far left and right ends of the x-axis. Okay, that's all. Goodbye.